Hello everyone. I would like to talk about the expectation and variance. So the outline of my talk is that I would like to talk about the reason to study, basic formulas, and the examples. So first, why we need to learn expectation and variance. So in many statistical packages, outputs do not provide all the information we need. For example, in regression, we cannot find the multiplied variance of dependent variables. So we need to calculate it, but books only provide some simple form of those equations, and that does not match what we need. So we need to derive the expectation and variance of some variable or statistic so we can use it. Reason number one is that think about the structural equation modeling packages. It provides some features to use the parameter estimates in the model to calculate the desired statistics. However, we need to know a proper equation. For example, I want to estimate the total dependent variable variance because it is used to calculate the coefficient of determination. However, instructional equation modeling is provide only the error variance, so we need some equation to calculate the total dependent variance. Second, sometimes simulation design requires us to manipulate some characteristics that cannot be plugged in equations directly. For example, I would like to manipulate the commonality, which is the proportion of true variance over the total variance within an item. Commonality is required to manipulate in my simulation, such that it manipulates the strength of association between indicators and factor. So I need to find some equation. I need to find some way to plug in the factor loading such that I got the desired commonalities. Third, we can use this knowledge that expectation and variance to derive the statistical formulas or biases in parameter estimates to understand the mechanism behind statistical tests. For example, I can derive the derivative coefficients from the factor analysis model. Or at least, we can understand what is going on in the method papers. This provides some derivation, and if we know some basic understanding of the expectation and variance, we can apprehend it. So expectation. In random sampling, we got the statistics, and statistics are varied across samples, so we know it is the sampling error. The expected value is the average of the statistics across samples, where the number of drawn approaches infinity. So let's see that. I have the parameter in the population, and I draw the first sample. I got the first statistics. Then I got the second sample. I got the second statistics, and so on. I draw it indefinitely. So if I can draw all possible samples, the expected value is the average of those statistics across all possible samples. If the statistic is unbiased, it means that the expected value of the statistic is exactly equal to the parameter. However, it is not always be the case. Let x and y be random variables and c be a constant. Notice that I use the green color to represent a constant. So the expected value of a random variable multiplied by a constant, you can isolate c out, and then you get this. So the expected value of x plus c equal to the expected value of x plus c outside the parentheses. and the expected value of x plus y is, you can just distribute it into expected value of x plus the expected value of y. And finally, the expected value of a constant is a constant. So, for example, I will use those equations to derive the expected value of x bar. So, think about that. Expected value of x bar equal to the formula of x bar 1 divided by n times the sum of the x. So we can isolate 1 over n out of the expected value, right, by this knowledge, and then we can distribute the expected value to individual random variables like this. Okay, so but we know in advance that x is independent and identically distributed. So x1, x2 until xn, it comes from the same distribution called x. So then we can just put it as e of x, and then we got n times e of x. Then we know that the expected value of x bar is equal to the expected value of x, right? Next, variance. The variety of statistics across sample is called the variance. So the square root of this variance is called the standard error. However, this is basically the same concept as the variance of variables, such that statistic is just one random draw of a variable. In this case, we call the square root of the variance as standard deviation. Okay? Think about the same situation, then variance is the measure of variability of statistics from all possible samples. The property of a good parameter estimate is that the variance of statistics should be as low as possible. Covariance means the measure of correlation between two statistics. So I got parameter 1 and parameter 2 from the same population. Then I can do a sample and I got two statistics. Then the covariance, the correlation of two statistics is called covariance. Like this, in this example, I find covariance of S1 and S sub 2. Let x be a random variable and c be a constant. So the variance of c times x is c squared times the variance of x. So when we isolate a constant from the variance equation, we got the square term. And the variance of a random variable plus a constant equals to the variance of the random variable. The variance of the sum of two random variables equal to the variance of the first term plus the variance of the second term plus 2 times the covariance of both variables. And the variance of a constant is 0 because constant means that we do not have any variance, right? Let's see the covariance. So let's x, y, and z be random variables and a and b be a constant. So the covariance of a times x and y equals a times the covariance of x and y. This is the same thing. If we put the constant in the second term, we can isolate that from the covariant term. The covariance of a plus x plus a and y equals to the covariance of x and y. This is the same thing if we add a constant in the second term, so it remains the same. And covariance of x plus y and z equal to covariance of x and z plus the covariance of y and z. This is the same thing as the covariance of x and y plus z equals to the covariance of x and y plus covariance of x and z. So let's make it a little complicated. So covariance of x plus y and z plus w equal to uh, we we got two terms in the first, two random variable in the first term, and we got two random variable in the second term. So the total elements in the right hand side of the equation is 2 times 2 equal 4. So covariance of x and z, covariance of y and z, covariance of x and w, and covariance of y and w. And the covariance of a constant and a random variable equals 0. So when we find the covariance of two sums that score, for example, the covariance of x plus y plus z and u plus v plus w. So my trick is that you put random variable in the first term as the rows of a matrix and random variables in the second term as columns of a matrix. Then you put the covariance of individual pair inside the matrix. Then the covariance of two sums is the sum of all cells, right? So this term equal to covariance of x and u, x and v, x and w, plus covariance of y and u, y and v, y and w, y and w, plus covariance of z and u, z and v, and z and w. For example, I would like to derive the variance of x bar. So the variance of x bar equal to the variance of 1 over n times the sum of the x. Then we can isolate n 1 over n out of the variant term. We need to square that because of this knowledge. Then we need to find the variance of the sum. So for example, if I have 5 elements inside that, I need to put x1 to x5 in the rows and x1 to x5 in the columns. So remember that variance is the covariance of itself. So because covariance of itself equal to variance, so the diagonal elements equal to the variance of individual term. And in the off diagonal elements, so think about that. Because each trial is independent and identically distributed, so x1 and x2 is covariant to be equal to 0, right? So the covariance of x sub I and x sub j equal to 0 if I is not equal to j. So all diagonal elements are 0. And then second, the variance of x sub n, so variance of any element of x equal to variance of x because they have identical distribution. So it should be something like this. So on the on diagonal element we had variance of x, and off diagonal element we have 0. So the variance of the sum of x equal to n times the variance of x, and then so the variance of x bar equal to 1 over n times variance of x, which is the variance of x divided by n. So find the covariance of x bar and y bar. So the covariance of x bar and y bar is the covariance of the 1 over n times the sum of x and 1 over n times the sum of y, right? And we can isolate 1 over n out of the covariant term. So we got 1 over n squared because the covariance of this knowledge, and we already know this, right? and we need to find the covariance of the sum of x and the sum of y. So I put x in the rows and y in the columns. Then I provide the covariance of each pair. Because each child is independent and identically distributed, so the covariance of x sub I and y sub j equals 0 if I is not equal to j. So the knowledge of one trial is not related to another trial because each trial is independent. And then on diagonal element, the covariance of x sub n and y sub n equal to covariance of x and y because both x and y in any n are identically distributed. It should be something like this, and so the covariance of the sum of x and the sum of y equals to n times the covariance of x and y. So that the covariance of x bar and y bar equal to n 1 over n squared times n times covariance of x and y. So equal to covariance of x and y over n. So right now we have some ideas how the expectation and variance and covariance works. From here, I will provide some examples that you can utilize this knowledge in many circumstances. So the very simple one is that we have simple regression. This is the equation that y equal to beta 0, which is the intercept, plus beta 1 times x. Beta 1 is the slope, and e is the error term. So we need to find the variance of y from the term on the right hand side. So the variance of y equal to the variance of beta 0 plus beta 1 times x plus e, right? And because we know that the beta 0 is the intercept, it is a constant. So we can remove it out from the variance terms. So we got the variance of beta 1 x plus e. So we need to distribute the variance term. So it equal to the variance of beta 1 x plus variance of e plus 2 times the covariance of beta 1 x and e. Right? And then we need to isolate beta 1 out of the x term. So it's equal to beta 1 square variance of x plus variance of the error term, and because the assumption of simple regression is that predictors is independent of the error term, so this covariance is 0. So we remove that from the equation and we get the result. For example, if we would like to specify the standard in simple regression, if we would like to specify the standardized regression as 0.3, 0.5, and 0.7, we need to find the residual variance. And we have another condition that we need to fix the variance of x equal to 1 and variance of y equal to 1. So from this equation, the variance of y equal to beta 1 square variance of x plus variance of the error term. So variance of y is 1, variance of x is 1. So we have 1 equal to beta 1 square plus variance of e. So the variance of e equal to 1 minus beta 1 square. That is beta 1 equal to 0.3, 0.5, and 0.7. So the variance of the error term would be 0.91, 0.75, and 0.51. We can put this, plug this in the equation that we would like to simulate some data. Next step, we have multiple regression, and we have multiple regression with 3 predictors, x, z, and w. Let's say we have y equal to beta 0, which is the intercept, plus beta 1x plus beta 2z plus beta 3w plus the error term. So we need to find the variance of y from the terms on the right hand side of the equation. So the variance of y equal to the variance of the right hand side of the equation. And because we know that the intercept is a constant, so we can remove that from the variance. Then we need to find the variance of the sum of 4 random variables. So I make the matrix and we get this, right? The variance, the covariance between beta 1x and beta 1x is beta 1 square times the variance of x, as well as the beta 2 square variance of z, beta 3 square variance of w, and then finally for the error term is equal to the variance of e. Then we need to find the covariance between those random variables. The covariance between beta 1x and beta 2z is beta 1, beta 2 covariance of z and x, right? The covariance between beta 3 w and beta 1x is beta 1, beta 3 covariance of w and x, and the covariance between beta 3 w and beta 2z is beta 2, beta 3 covariance of w and z, right? These three terms equals to these three terms because the covariance matrix is symmetric, and the error term is independent to all predictors, so these elements are 0. So the variance of y is equal to the sum of all elements in the matrix. So equal to beta 1 square variance of x, beta 2 square variance of z, and plus beta 3 square variance of w plus variance of e. These are all on the diagonal elements. Then we add of diagonal elements, so plus 2 beta 1 beta 2 covariance of z and x, 2 beta 1 beta 3 covariance of w and x, plus 2 beta 2 beta 3 covariance of w and z. So we can use this knowledge to find the confidence interval of the adjusted R-square. So we need to write equation of adjusted R-square and use SEM package to estimate the standard error of the adjusted R-square. Okay, so let me show you the M plus script. So because we forget about R right now, and let's say that okay, I use M plus script, and I think this is easier to understand. So for the y on x, we name it as beta 1, the regression coefficient of y on z. I name it as b2, and regression of y on w, I name it as b3. So the variance of y, the variance of the error term is ve. Variance of x is variance of x, variance of z is vz, and variance of w is vw, as well as the covariances of predictors. Adjusted R-square can be calculated by this formula. So we need to know n and p, right? N equal to 200 on this example, and p equal to 3 because we have x, z, and w. So we know the equation of the variance of y equal to something over here. Then we need to calculate the variance of y and the variance of the predictors to get the R-square, and then use the R-square to calculate the adjusted R-square. So in the model constraint in the M+, I have variance of x, variance of all x, so variance of all predictors, variance of y, R-square, and adjusted R-square. These, for this, I would like to derive it by the formula. So the variance of x equal to beta 1 square times variance of x, right? beta 2 square times the variance of z, beta 3 square times the variance of u, plus 2 times beta 1, beta 2, covariance of h and c, 2 times beta 1, beta 3, plus the covariance of xw, and 2 times beta 2, beta 3, and covariance of w and c. So the variance of y equals to the variance of all predictors plus the variance of the error term. So the r squared equal to the variance of all predictors over the variance of y. And then we can calculate the adjusted r squared like this. So when we run this script in the m plus will provide the standard error of the adjusted r squared for us, and then we can use that for finding the confidence interval of the adjusted r squared. So the next step, I would like to show you the simple mediation model such that m is predicted by x. So I sub 1 is the intercept and a is the slope from x to m, and d is the error term, and y equals to I2, which is the intercept, plus b times m, where b is the slope of m to y, and c prime is the slope from x to y, plus the error term. So I would like to find the variance of y via variance of x, variance of d, and variance of e. So variance of the predictor x, right? Variance of d, which is the error term of the mediator, and variance of e, which is the error term of the y dependent variable. So I need to combine these two equations to a single equation. So I substitute m over here by the term on the right hand side, and then I distribute that, and I get this formula. So I am very sorry. So if we would like to focus the effect of x on y, we can combine this equation like this. So this is the intercept of the slope from x to y, and beta 1 plus beta 3 times c is the slope of x to y given the c value. So I can write down the equation such as y equal to beta 0 given c equals z. Big C equal to small c. So big C is the random variable and small c is the any c value, a constant, plus b1 given big C equal to small c times x1 plus e. So if I would like to find the standard error of the slope of x at c big C equal to small c, so the variance of b1 given c equals c. So you see I have this hat because it is estimated from sample, and because it is estimated from sample, we have sampling error, and we would like to find the standard error of this term, right? So the beta 1 given big C equal to small c equal to the variance of beta 1 hat plus beta 3 hat times c. So because c is given, then we can isolate it out, and we can find it is the variance of the estimate of b1 plus c squared, and the variance of the estimate of b3 plus 2 times c times the covariance of is the estimate of b1 and the estimate of b3. Let's probing the following result. So I made the LM command such that y is predicted by x times c, and I got this equation, and I found that the interaction was significant. So I would like to find the slope of y on c as c equals 1. So I need to find the variance of the estimate of B1, the variance of the estimate of B3, which can be found the by this standard error square, right? But in this output, we cannot find the covariance of the estimate of B1 and the estimate of B3. So we can use the vcov function to get that. And this is the vcov function. And we got this, the covariance matrix of the parameter estimate. So from this, we can guess this is the variance of B1 hat. This is the variance of B3 hat, and this is the covariance of B1 hat and B3 hat, right? So I can calculate that and see, we know that it is equal to 1. So we get the variance of B1 given C equal to 1 equal to 0.1616. And we can make the statistical test for whether B1 given C equal 1 was significant or not. So final example, we need to derive the reliability formula from the CFA model. So we get this model. We have a simple factor analysis model such that we have only one factor explain all 5 variables, and this is the factor loadings, and we have the error term of each observed variable x. And from the classical test theory, we know that x each observed variable equal to the true score and the error score, right? And true score, which is the f times the factor loading, that is lambda j factor I. So j represent the number of items and I represent individuals, plus the error term epsilon ij times 1 from here. So because 1 times anything is anything, so and y is the sum of all x, so which is the sum across item of all true score and the error score. And we know that true score equal to lambda j times factor I plus the error term of each item. Then because f does not vary across items, so we can isolate f out. Then f sub I times the sum of the factor loading plus the sum of all error terms. Okay? So in the reliability row, we would like to estimate the variance of the true score for over the variance of all observed variable. So it's equal to the variance of blue thing over the variance of blue thing plus the variance of red things. Okay, so let me erase all ink from the slide, and then we get the true score, right? Which is this from the previous slide, and the variance of y equal to this. Okay, so this is the true part. So we need to derive the formula, and this is the error part. So because f is independent from all error term, and all error terms are independent from each other. So from this equation, we can isolate sigma, the sum of all factor loading out from the variance term. So don't forget to have the square term. And then because f and all epsilon are independent. So we don't have any covariance between f and any error term or the covariance of any error term because they are all independent, right? We get this formula, then this is the formula for the derivative when we calculate it from that factor analysis model. Sometimes we call coefficient omega for this formula of the reliability. So let's talk about our example. Okay, I have the simulation and my design condition in the CFA are as follows. So I would like to have the reliability between 0.7 or 0.8 or 0.9, and the number of items are 4, 6 or 8. Then I have two conditions over here, right? I would like to have factor loadings and error variance to be equal across groups. And then to get the factor identification, I fix the factor variance to 1. And our indicator variance in this simulation, I set it as 1. So I would like to find lambda and sigma square for each condition, for each reliability and the number of items. So first, because we have equal factor loading and equal error variance, so from this formula, we can get this because all lambda are equal. So it's equal to j lambda, and don't forget to have the square. The variance of the factor equals to 1 because of the identification. This one equal to j lambda square, and because the variance of the error term are equal across item, so this one equal to sigma square, and the sum of sigma square across j equal to j sigma square, which is this. Okay, let me delete the ink, and then given that indicator variance is set to 1, so x is lambda j factor I plus the epsilon, right? So because f and the epsilon are independent, so we get this formula, lambda square j variance of f sub I plus variance of the error term of x. So this one equal to 1 and this one equal to sigma square, and so we get variance of x sub j, and because we set the indicator variance to 1, so we have 1 over here equal to lambda square plus sigma square. So we can move it around so that sigma square equal to 1 minus lambda square. We can substitute it to, so here we get this, right? And we can simplify this equation, so we get this. Rho can be calculated by j times lambda square over j lambda square minus lambda square plus 1. And that is, I isolate lambda into the left hand side, so I get lambda equal to the square root of this ratio. And if you like to find the sigma square, is equal to 1 minus lambda square. And I fix lambda to be only in the positive value. Okay? So I substitute 0.7, 0.8, and 0.9 to this row, and j, I substitute 4, 6, and 8. So I got this 0.7, 0.8, 0.9, 4, 6, and 8, right? And I get the value of lambda and sigma square. So thank you very much. So I just introduced you how to estimate the expectation and variance of some complicated equations. So please leave the question on the comments on this video. So your question will be very helpful for me and other viewers of this video. Thank you very much.